Joule heating is commonly used to model electric heaters and light bulbs. Hello, I'm Armin, and welcome back to my channel. In this video, I'll show you how to couple electric currents and heat transfer to model a wire and compute the temperature distribution. Let's take a look at the model before we get started. Joule heating, sometimes called resistive heating, happens when an electric current passes through a material that has electrical resistance, and part of the electrical energy is turned into heat. At the microscopic level, this heat is generated because moving charge carriers collide with the atoms of the material and lose energy. We see Joule heating in many everyday and industrial applications, such as electric heaters, furnaces, filament lamps, welding systems, and thermal actuators, where electrical energy is intentionally converted into heat for practical use. The governing equations include heat transfer with radiation and Ohm's law. Ohm's law relates the current density J to the electric field E. The heat generation rate due to Joule heating is then calculated from J times E. The heat transfer equation describes how this generated power is distributed through conduction, using Fourier's law, and through radiation. A copper wire with a radius of 0.01 millimeters and a length of 10 millimeters is subjected to a 0.1 volt potential difference in the electric current's physics interface. Heat is generated due to Joule heating, and thermal radiation with an emissivity of 0.3 dissipates heat to the ambient through the Surface-to-Ambient Radiation feature in the Heat Transfer in Solids interface. A stationary study is used because the solution corresponds to steady-state conditions. The analytical solution is calculated using the material properties listed in the table. The numerical results show excellent agreement with the analytical values for temperature, electric field, and generated power. Next, the straight copper wire is replaced with a helical geometry, and the model is solved again. This allows us to evaluate the electric field and temperature distribution in a more complex configuration. The explanation is sufficient, so let's get started.
At this point, I click on Model Wizard. Since the model is three-dimensional, I select 3D. As mentioned earlier, this simulation involves Joule heating, so I expand the heat transfer section. Under the Electromagnetic Heating section, I select Joule heating. I click Add to include this physics interface. In the Added Physics Interfaces window, we can see electric currents and heat transfer in solids. These two interfaces are coupled through electromagnetic heating. Next, I click on Study to select the solver. Because this is a steady-state simulation, I choose a stationary study. Finally, I click Done. The first step in any simulation is usually creating the geometry. Before doing that, it is better to change the length unit from meters to millimeters. We need a very thin cylinder to represent the wire. I right-click on Geometry 1 and select Cylinder. For the axis direction, I change it to the x-axis.
I set the radius to 0.01 millimeters and the height to 10 millimeters, then click Build All Objects.
Now we have a long, narrow cylindrical geometry that represents the wire.
I'll click on Zoom Extents to see the whole geometry. The next step is defining the material. I right-click on Materials and select Add Material from Library. In the Built-in section, there are many available materials to choose from. For this simulation, I select copper, which is suitable for Joule heating analysis. Then I click Add to Component. Since no other materials are required, I close the Add Material window. The Material Contents section now lists all material properties. For these physics interfaces, 5 material properties are required. However, in a steady-state simulation, properties such as heat capacity and density are not critical. Even so, they are still included,
as indicated by the blue check marks. Now let's define the boundary conditions. I'll start with the electric currents physics interface. I go to the Physics tab, where boundary conditions can be applied to domains, boundaries, edges, or points. I expand boundaries and select electric potential. I apply the electric potential to the left side of the wire. Here, I set the potential to 0.1 volt.
The other side of the wire is ground, which corresponds to 0 electric potential. I go to Boundaries again and select Ground. As a result, the potential difference across the wire is 0.1 volts.
Now I'll define the boundary conditions for heat transfer in solids. This section includes the reference temperature, and I leave it unchanged. You can modify this value based on your environmental conditions. The wire heats up to a very high temperature, for example around 1000 Kelvin. At this temperature level, thermal radiation becomes the dominant heat transfer mechanism. Therefore, convective heat transfer can be neglected. I expand boundaries and select Surface-to-Ambient Radiation. Then I select the lateral surfaces of the wire. The ambient temperature must be consistent with the reference temperature. I keep both values unchanged. However, the surface emissivity is not defined for copper by default, so I change it from material to user-defined and specify a value. Here I set the emissivity to 0.3. This value is material dependent and can vary based on surface condition. In the Multiphysics node, no changes are required. If I open Electromagnetic Heating 1, we can confirm that the electric currents domain is properly coupled with heat transfer in solids. This coupling allows the Joule heating generated by the electric current to act as a heat source in the solid domain. The next step is defining the mesh. I click on Mesh 1, where 4 contributors are listed: electromagnetic heating, heat transfer, electric currents, and geometric analysis. This geometric analysis feature is available only in newer versions of COMSOL. I click Build All. The geometric analysis automatically estimates a suitable mesh for this model. If you are using an earlier COMSOL version, you must define the mesh manually. Because the wire has a very small cross-section compared to its length, an automatically generated mesh without geometric analysis may be inadequate. I enable geometric analysis again and click Build All. At this point, everything is set up correctly. Now we can solve the model. I go to Study 1, click Compute, and wait for the solution to complete.
The solution is now complete. By default, the electric potential result is generated. As expected, the applied potential is 0.1 volts, which matches the value we specified in the electric potential boundary condition. The electric field magnitude is the electric potential divided by the wire length. In this case, the value is 10 volts per meter, which is correct. Next, let's look at the temperature distribution. The maximum temperature is approximately 1150 Kelvin. This result matches the analytical solution, so the model is validated. Now let's move to a more complex geometry. Instead of a straight wire, I'll use a helical wire. I right-click on the geometry node, go to More Primitives, and then choose Helix. I set the number of turns to 5. The major radius is 0.5 millimeters. The minor radius corresponds to the wire radius, which is 0.1 millimeters, the same as before. I also set the axial pitch to 0.1 millimeters. Then I click Build Selected. At this point, I disable or delete the previous cylindrical geometry. Next, I define the electric boundary conditions. I apply electric potential to the lower cross-section of the helix. The upper cross-section is assigned ground. Now I update the surface-to-ambient radiation boundary condition. I remove the previous selections and apply it only to the lateral surfaces of the helical wire. To avoid excessive heating, I reduce the applied electric potential to 0.05 volts. I go to Mesh 1 and click Build All. The mesh is generated successfully. Now I solve the model. I open Study 1 and click Compute. The solution is complete. The electric potential corresponds to the difference between the applied potential and ground. Again, the electric field follows from the potential difference divided by the effective wire length. Now let's check the temperature. The maximum temperature is approximately 657 Kelvin. The temperature distribution is relatively uniform along the wire. This happens because the surface-to-ambient radiation boundary condition is applied uniformly over the entire lateral surface, resulting in similar radiative heat loss everywhere. This brings us to the end of the tutorial. Thank you for watching.